Barati Farimani. He is the Russell Trader Associate Professor of Mechanical Engineering at Carnegie Mellon University. He joined the Department of Mechanical Engineering at Carnegie Mellon in the fall of 2018. Before that, he was a postdoctoral fellow at Stanford, working with Professor Pandey on artificial intelligence and drug design. He received his PhD in mechanical engineering in 2015 from University of Illinois at Urbana-Champaign. His group focuses on the problems at the interface of engineering, data science, and machine learning. He develops the state-of-the-art deep learning and machine learning algorithms and tools to learn, infer, and predict the physical phenomena. He received many awards, including the Stanley I. Weiss Best Thesis Award from University of Illinois in 2016, and was also recognized as the outstanding graduate student in 2015. During his postdoctoral fellowship at Stanford, Dr. Barati Farimani has developed data-driven deep learning techniques for inferring, modeling, and simulating the physics of transport phenomena and for materials discovery for biology and energy harvesting applications. The floor is yours, Amir.
Thank you so very much, Mehmet and Josh and Professor Khadim Hosseini for the invitation. It's an honor to present in Terasaki Institute. I've always seen great developments at the Institute, and the results that are coming out are marvelous. So today I'm going to talk about, deep learning in general in biological discovery and recent advances that has happened during the past couple of years, specifically large language models and the word of GPT or generative pre-trained transformer models, and then I'll showcase how they can be used for biological discoveries. So one of the biggest and important tasks in biological discovery is a small molecule discovery, or effectively drug design or drug discovery. And for that, we need to do a lot of effort. So it's a kind of like 15 years effort in different aspects. So first, target validation, compound screening, lead optimization, some preclinical tests, phase 1, phase 2, phase 3 clinical. And it's taking like billions of dollars, like 15 years of developments for discovering a single drug. And it's very time consuming and it's very expensive process. So the question is that how difficult the process is and what are the bottlenecks in this drug discovery effort. And to be honest, it's like a needle in a haystack, because with a few organic atoms that you have in the periodic table, you are able to build something around 10 to the power of 60 molecules. And you wanted to look, to find one of them which works the best for the target that you have. And effectively, AI and, machine learning can be a great solution. Why? Because neural networks effectively are called universal function approximators. So they are effectively can go from a molecule to the property directly. They can estimate, we can find a functional form that effectively is able to do that. So, and to predict the properties. So for example, we need to say if a molecule is toxic or not toxic, if a molecule is soluble or not soluble, if a molecule is penetrating the brain-blood barrier. So these are the things that before we send the drug to the synthesis and assay screening or animal studies, we need to know about these drugs. And these tests, for example, toxicity is very expensive. And this is the first thing to know. And the question is that can we build an AI model for that to predict rapidly in a flash of seconds, is less than a second, if this molecule toxic or not toxic. That helps us accelerate the process of discovery to a large extent. So if that is the problem, obviously a lot of people have been trying to build machine learning models for what we call molecular property prediction. And before the era of deep learning, before the 2012, there have been an array of different kind of methods, for example, support vector machines, kernel, Bayesian ensemble. And most of these, they are not a type of end-to-end models, effectively, you need to create a nice descriptor or feature about a molecular structure to represent it, and then give it to one of these ML methods that I listed here to predict the properties. And properties can be, for example, toxicity, can be, solubility, any kind of these properties. But we have challenges that hinders the field to a large extent. The first challenge in molecular machine learning is the enormous magnitude of chemical space. As I mentioned before, there are the size of like 10 to the power of 30 or 10 to the power of 60 between this range of potential pharmacologically active molecules. So we are working with such a huge space. You can see that, for example, we have a data set called GDB17, which you have 111 actually billion types of molecules. And these molecules are all potential active molecules that you can use. So the first challenge is the enormous space. And if you wanted to run experiment for each of these single molecules, then you will never get actually the results in time for development of a drug. It takes like years and years. The second problem is insufficient and noisy label. Labels are very expensive in biology. In general, labels are very expensive in biology. And for any machine learning algorithm, you need to have great data sets and great labels. So for example, if you wanted to find out a cancerous or non-cancerous cell, you need to do a lot of tests, for example, to do that, to find that. It's not as easy as cats and dogs or images that in a millisecond, as soon as you see it's a cat, it's a dog, it's very easy to do that, for simple images. But for example, for a molecule, if you want to say if it's toxic or not toxic, you should definitely run some kind of like very expensive simulations, or you need to run wet lab experiments to know if it is toxic or not toxic. If you wanted to measure the solubility, it's also very difficult experiments. And then with this huge amount of space that we have, and then also the labels that we don't have, and effectively it needs a lot of experiments. So how can we solve this challenge, or how can we solve this problem? Is there a solution? So that's what my lab has been focused on. So we have seen a growing actually number of compounds, uh, and these are without labels. Effectively in PubChem, we can see that there are a lot of valid molecules that are there. There is this angular distribution in any one, so we have like millions of different kind of structures of the molecules. We have the PDB data set, which is the protein data bank. You can see a lot of different structure of the proteins, G protein coupled receptors, kinases, channels. They are growing as the crystallography and cryo-EM is getting evolved and evolve more. So we have a lot of data, but all these data, they don't have labels, right? So I have a molecule which is good, but I don't know if it is toxic or not toxic. So the question is that, can we make use of this large unlabeled data for better ML molecular representation? So that's the key question. And the answer is yes. We can do that with something called self-supervised learning. So you have heard about the supervised learning. You have heard about unsupervised learning. So today I want to talk about self-supervised learning. And to be honest, to be much more frank about like what's going on, this is exactly the P of the Chat GPT. So we call it pre-training. So there are a lot of interchangeable words used for the SSL. Pre-training, the P of Chat GPT that most of you are using is one of them. So what is this about? Let me explain a little bit in context of what is supervised learning versus self-supervised learning versus supervised learning. So in supervised learning, you know that, for example, you have the images of a cat and dog. And for example, cat, you can see here, you do the manual annotation. And then you have X, which is the image, and you have Y, which is the label, cat, dog, cat. And then this is called supervised learning, which is the general methodology for learning. For learning the labels for the images. But in self-supervised learning, we consider that we don't have labels, so we don't know if it is a cat or dog. But what we can do, we can play around with the data, the X itself, and for example, rotate it like 90 degree, 180 degree. This is one of the examples of the self-supervised learning, and create the label from the image itself. So effectively, you can see the label here for this image. You don't need to know it's a cat or dog. It's 0, the label for this image is 90, and the label for this image is 180. What I did is that I wrote a computer a script, for example, that rotates the image. And then with that, effectively, you can learn the if you run a network and do this kind of, like, for example, classification task of images, you can learn the representation or the features that are assigned to each image that you have. Okay, so this technique is called self-supervised learning, in which you can create the label from the data, from the X, without actually spending money or expensive time, I mean, in order to make the real labels. And so inspired by this technique in vision and language, also in language we have that I'll explain later on, we can have the SSL pre-training, which we have unlabeled databases of molecules that I showed you, and have an SSL objective, which is like, for example, here degrees. There we have an objective that I'll show you later. And then what you can do is that you can warm up the parameters of your neural networks with that, and then do something that some folks call it transfer learning. This is another name for also self-supervised learning. And then use the label data set, and you can fine tune, your label data set to the property prediction. Okay, so that's great. I mean, effectively, you don't need to use a lot of data points. So to that end, I mean, in 2021, we created the first molecular contrastive learning framework, in which we took advantage of one of the self-supervised learning algorithm called contrastive learning. And I'll explain what is contrastive learning. So if you have a molecule and you have their SMILES, for example, SMILES one, so you can show the molecule like this. You can build the graph. So for example, a molecular graph G1 and molecular graph Gn. And then what you can do the augmentation. So you can do the graph augmentation. But what does it mean? It means that, for example, you can take two copies of this molecule, the same molecule, and then mask some part of the bonds or angles or atoms. And here you can have another molecule. You can mask some bonds, some angles, some atoms, and then send it to a graph neural networks, in which it is encoding it to the landscape, to the latent space, and then you can get an encoded space. This is effectively, if you have heard about PCA, it's similar to that. It's kind of like principal component space in the latent dimension. And then what you can do is that you can do the contrastive loss. So effectively, these two molecules that are the copy of each other with a little bit changes, they are the same. So in the latent space, you can lock them to each other. You can tell the network that, hey, these two molecules, I a little bit added noise. For example, I removed or some part of it or added something, but still they are the same roughly. And then you can do these things for the molecules that are not similar to each other. You can say, oh yeah, these two molecules are not similar to each other. So how we can do that? First of all, you can do the different kind of augmentation. For example, for a molecule, to make different copies of that molecule, you can, for example, do the atom masking, in which you delete an atom. You can do the bond deletion, you delete a bond, for example. And you do the subgraph removal, in which you remove some of the graphs, and then you can pass it to the graph neural networks, right? So you have a graph neural networks that is encoding it to the latent space. Okay, cool. And then here I wanted to explain to you what is called contrastive learning. So contrastive learning, what it says is that you have a molecule, you do augmentation either by masking some of the bonds, and then you take it with using the neural network to the latent space. So you put a point here. You do another augmentation, you use the graph neural network, you have another point here in the space. And then you say that these two molecules are the same. I a little bit perturb them. So they should attract each other. You have another molecule on this side, you can see, you do the augmentation, you have this point, and then you say this molecule is not the same as this molecule, so they should repel each other. So to that end, effectively, we have a loss function, which is called normalized temperature scaled cross entropy loss, in which you calculate the cosine similarity between these 2 points that should attract each other. Here, as you can see, Zi and Vj are the two molecules. And if I and J are similar to each other, they are the same molecule. So the cosine similarity should be similar to each other, right? I mean, so the cosine similarity should be 1 because the angle between them is 0. And then for the molecules that are repelling, this is not 1, okay? So what we did in our lab, actually, we trained using this for the first time, actually, back in 2021. We pre-trained it on 10 million molecules from PubChem. And we pre-trained it, and then we got a graph neural network, which is pre-trained with a lot of molecules. And then we tested, for example, to see how much, to what extent it learned the representation of a molecule, how good it can understand what is each molecule. And then if you look at it, for example, if you color all these molecules, this is the landscape in the latent space. If you color it by different color, for example, molecular weight, you can see the clusters of, for example, molecular weights. Then what you can do is that you can test, so you have a network which is pre-trained, and this is super warmed up. So effectively in the optimization landscape, you are somewhere closer to the local minima, as opposed to the case that you initialize the weight using, for example, Javier or Glorot. So for molecular net benchmarks, we use different kind of data sets that actually has been used when I was at Stanford. In VJ's lab, we have this benchmark of which we call molecule net, and we have quantum mechanics data set, we have physical chemistry data set, we have biophysics and physiology. So we developed graph convolutional neural network with the backbone and GIN, and we did actually different types of ablation studies and comparison with different types of architectures. And we saw that, okay, yeah, like this pre-training is effectively working, and it gives us a better result. For example, molecular with the backbone of graph neural network that we have, you can see that its accuracy for classification is pretty high. And by the way, each of these benchmark, this triple BP is a data set for classification if a molecule is penetrating the brain-blood barrier. Tox21 is a toxicity data set effectively. CleanTox is a toxicity data set. HIV is a data set that shows if a molecule can be used for HIV or not, and different kind of data sets here. We did also so these are classification tasks, and we measure their accuracy by ROC AUC in percentage, and also we tried this on the regression task. So for example, solubility is a regression task. So we measured the solubility in freesolve and esolve data sets, for example, for quantum mechanics data set, lipophilicity, and we see that it is doing good, but not as super good as what we see in classification. And the reason is that, for example, when you do the data augmentation, even for images, you have a cat, you chop the ear of a cat, or you add a little bit noise, it's still a cat. So the class doesn't change. A cat doesn't become dog when you perturb the image. Even if you cut the half of an image of a cat, it's still a cat. I mean, our eyes see it's a cat. But solubility is a regression test. So your label is continuous. Whenever you are changing a little bit the X, which is the molecule type, the label is also perturbed. If it is like 20% soluble, it becomes 25% soluble or 15% soluble. That's why we don't get the amazing results that we get for the classification task, like solubility. Also, we did like this ablation study on augmentation. So what does it mean? It means that, okay, you may wonder yourself that, okay, if I can mask a molecule, to what extent can I mask it? Is it like 10%, 5%, 25%, 50%? How much can I remove the number of atoms? Because it can be endless, like till you delete the whole molecule. So we did it like with like 25%, less than 25%. 25%. And as you can see, the results are interesting. For example, for the ClinTox data set, the rock AUC, as you see, for example, for the subgraph removal, for the 25%, you get a good result. So roughly like 25% perturbing the molecule is okay. And actually, that's kind of like exercise, a great exercise for learning. Okay, great. So the second things that I wanted to talk a little bit about is using transformers for chemical compounds. So for example, in many applications in biology, we are using polymers. I know that there are a lot of studies using hydrogels and polymers in tissue engineering, regenerative medicine that Terasaki Institute is doing. And one of the big questions is that can we design a polymer using AI? And machine learning. And in designing or metal organic frameworks, these are the material science actually type of questions. And for polymer, you know, I mean, we have different types of polymer. We have linear polymer, we have branch polymers, cross-link polymers, network polymers. We have also copolymers, which we have graphs or alternating or random polymers. And then always we have this significant geometrical information of the polymers, which most of the time is not available. The question is that, oh, wow, I mean, if I wanted to model this polymer or find out the property of that polymer, I don't have the information of the structure, because the structure you need to run a lot of, you know, imaging and other techniques to get the structure of a polymer. So the question is that can we use language? Can we use language model in order to model and design and predict the property of a polymer? And that's what we did in this paper in Nature Computational Material in 2023. And we created something which is called transformer-based language model for polymers. What we did is that we thought that for different polymer studies, we have polymer number 1, we have copolymer, and then you can show a polymer monomer with, for example, a SMILES. So a SMILES notation is a way that you can show a structure. Even you don't need to know the structure. You just need to know the formula of the polymer. And then you also have some experimental values. For example, the ratio of polymer to the copolymer, the type of polymer, the tag. Also, you may have a different temperature for the experiment, so you can include the experimental data as well, you know, to your to the design that we have. And this is like, I mean, describing, you know, the system that you are doing experiment using language. So you can create a kind of like a few sentences, as you can see here, and then you can tokenize it. So tokenization is effectively like featureizing, you know, the space in order to make it ready for the transformer. And then what we did is that we used the same trick that we used in the previous section of my talk. So first of all, we created something around 1 million polymer using the data augmentation, and effectively we used the mask language model in order to pre-train something what we call transpolymer. So effectively we warmed up the weight of this neural network. And then this is the self-supervised learning part, or the pre-training part of it, which is very similar to the Chat GPT-P. And then what we did is that we transferred the weight and fine tune it, means, I mean, like do the real supervised learning task with the regressor head, and we went to the properties. So you give me a polymer sequence, I give you some properties. The property can be anything. It can be a dielectric constant, it can be, for example, band gap, whatever property you may imagine. So we are building a general engine that learns the polymer representation. And this is what we call it transpolymer. And then during the fine tuning, what you do is that you specifically build a model, for example, for that property. So you use that general pre-trained model, which we call transpolymer, and you fine tune it for conductivity. You fine tune it for band gap. You fine tune it for electron affinity, ionization energy, everything like that. And then, and here is the number of data points that you need. And we saw that without and with pre-training, there's a tremendous shift in the accuracy. So for example, you can see that we were able to bring down 52% the root mean square errors, or 23%, sometimes 30%. And this was significantly large in terms of how much you can decrease or shut down the amount of error because of the pre-training. And specifically with this a small amount of data. So before this, when I was approaching the companies, polymer companies, and I asked them, I can build a model, polymer model for property prediction for you. And one of the key questions they asked me was, how many data points you need? And I said, okay, before pre-training, I was saying 10,000, like 20,000, 100,000. And they said, no, I mean, we are not going to work with you because we can't do 10,000 experiments. But now with the transpolymer and these huge pre-trained models, we only need like 271 samples, or like, I mean, 561 or 368. So the regime or the number of data points that you need is much, much smaller. And that's a great news for, merging experiments with AI, because experimentation is very difficult. And if the AI folks wanted to collaborate with the experimentalists, they always need a lot of data, the AI people. Now with these techniques of pre-training, you need less data. And that's a great news, about the collaboration between experimentalists and AI people. And that's the message I wanted just to relay here. Specifically, this might be very interesting to the Terasaki folks and the research scientists, that nowadays, with less amount of data, we AI people can collaborate with you and predict the properties or do whatever you like with much, much, much less amount of data. And this is a kind of like progress that has happened because of the pre-training and self-supervised learning. And I'll explain why. So you can see that if you pre-train with 5K versus 5 million, look at the difference. For example, like with 5 million, the R squared goes to like 70%. With 5K, it is here. You see, I mean, there are differences. And the reason is that this is a golden sentence. Pre-training data fills the knowledge gap. So the gray data points you see in the background is the latent space representation of polymers with 5K here, with 50K, and with 1 million. You can see that, I mean, like with 5K pre-training, this valley that is wide, I mean, there's an information gap. There's an information gap, and that information gap causes huge amount of error. As you pre-train more, you can see that, okay, you are feeling more, the knowledge gap. And then if you do it with 1 million, you see that almost you have covered the whole space. It's like very similar to the chemist. So for example, a person, if you wanted to train, if you wanted to, a chemist to predict the property of a polymer, if that chemist already has a lot of knowledge of polymers versus a high school student who doesn't have, for example, a vast knowledge of, for example, polymers. That's the difference. So that scientist, that polymer scientist, you take him to the or her to the lab, and with 3 days training, he or she will be very good at predicting, for example, the band gap or a property, because he has a knowledge. He knows polymers. He knows how they are working, their structures, stuff like that. The gray area is exactly similar to that. So this, like 1 million pre-training, is like a very, very knowledgeable polymer chemist who goes to the lab and does each of these tasks, I mean, with a few fine-tuning steps. Okay, great. So I'm going to shift a little bit now in the second part of my talk about a renaissance that is happening in sequence-based therapy on the protein language models. The first part of my talk was about the small molecule and polymers, the two things that are very much needed in the world of biological discovery. Now, I want to talk a little bit about proteins and protein language model. I hope that it is useful for you. And I mean, sequence-based therapy is very fashionable these days. It's becoming into existence. We have now anti-cancer peptides. We do the antibody conjugates and adjuvants that we are designing. We are designing antibody fragments. We are designing some sort of that. So it's effectively as opposed to a small molecules, which you're having a chemical compounds, you're using the amino acid blocks of the sequences, make a short peptide for the drug discovery for as a drug, and they obviously have a lot of benefits. Like, I mean, the benefits are obviously they are native to the body, right? I mean, you don't need to synthesize them. That's the biggest benefit. A small molecule, you need to synthesize if it is synthesizable, if it is stable or not stable in large amount for manufacturing. But the sequence-based therapy, I mean, it's a couple of amino acids. You just express them into the cell, and then you get whatever peptides you want. But they have their own problems. For example, they aggregate in the body. They will not hemolyze very well. They may go and bind to other entities that are unknown. And the design of them is also not that much easy. So the design of this sequence is not that much easy. The reasons are that you need the structure. Most of the time, you need to know the X-ray crystallography structure of a peptide, and then dock it or put it inside the protein to see if it is binding from the structural protein design. And then the question is that can we use only the sequence, like AC, for example, KLMN? You give this sequence, and you know the property of this molecule. If this protein or peptide, is it, for example, toxic or not toxic? Is it hemolyzable or not hemolyzable? Is it aggregating or non-aggregating? Is it fouling or not fouling? So that's the question. And then there's something that came out in the last 3 years, which is called protein language model, which actually you can represent a protein as a language model. And this is not something new. During the past like 20 years, we had this thing that is happening. And then there were a lot of different ways. For example, you wanted to have, I mean, so for normal language, you have a text, for example, the cat sat on the mat. So you have a start there. I mean, so you can represent it like this, tokenize it. And then you have, for example, a protein sequence like MSTI, YSTGK. And then you can represent it like this. And then you can use machine learning, like, I mean, support vector machine or random forest, those classical, traditional, what I call shallow machine learning techniques, to predict the properties. But with the rise of transformer in 2018, with this beautiful paper from Vaswani that has transformed everything. So whatever we have in ChatGPT and DeepSeek and everything that you see these days is all based on transformers, and transformers have solved the problem of sequential computing. So for example, if before before transformers, you wanted to say if a book is romantic or drama or classify that, you use something called backpropagation in time with the LSTMs or recurrent neural networks. And that had a lot of problems. What was the problem? The problem was that one of these small gradients or big gradients actually killed the overall signal of learning. And you needed to backpropagate from the last word of the book, for example, Shakespeare book to the first word, and somewhere in the middle, the gradient was small and it kills the signal. But now with the transformer architecture, thanks to Google people and especially mass language model, this is another big invention which is called BERT. It's now possible to actually model the language. And you can see the huge, marvelous ChatGPT and DeepSeek and all these technologies, Llama, they are all relying on the transformers and mass language model. And transformers have been used immediately since their existence in 2018 in different things, like, I mean, vision, even the vision that we were using, ResNet and, for example, AlexNet, it has been revolutionized and people are using VIT these days, which is a vision transformer. In autoencoding, also in science, we have a SmilesBERT in which, I mean, this is a foundation model for learning the representation of the molecules, and also ESM1, I mean, AlphaFold, and like, I mean, these kind of like sequence to structure prediction techniques that are published in Science and Nature. All of them are based on the transformers. So I talked about T of the ChatGPT. I wanted to talk a little bit about P, which is pre-training. I already talked about it actually in the first half part of my talk, but it's very interesting that how ChatGPT is working without the unlabeled data, or effectively with the unlabeled data and without the need to the labeled data. And one of the simple things to do is to just create a, for example, masked words and tell the network, okay, what is the multiple choice question here? Go and predict this task, you know, and then you can run it on tremendously large corpus of unlabeled text. And then you can do the fine tuning as I explained before. And then, and for example, you can predict, for example, the topic of this book is about biology and get a huge accuracy. So, and then why protein language models matter and how you can do that. Effectively, you can use the same technology, which is P, and then also the transformers, and build actually the protein GPT or protein BERT, which is the language model for the proteins. And then these have revolutionized the way that also we are modeling the proteins and we are predicting the properties of the proteins. So effectively, instead of words, you can just present the sequence of the proteins and then use the transformers and do huge amount of pre-training by masking and build the foundation models of proteins. If you search online, for example, protein BERT or protein GPT, there are tons of models that are coming out in Hugging Face and other places you can find them. So inspired by that, my lab created something called peptide BERT. So what we did in peptide BERT, which the paper is here, we use one of these general engines of protein language models. In short form, we call them PLM. You can go and get them from Hugging Face. There are different versions. There's ProtBERT, there is Protein BERT, there is protein, I don't know, Bertology. There are different types of them. And then you can get one of them, and then you can run it on different kind of data sets. For example, there is a data set for peptides that are saying if, for classification, if a peptide is hemolysable or not, if a peptide is fouling or non-fouling, if a peptide is soluble or not soluble. And then you can attach like 2 layers of neural networks or 3 layers of neural network to this multi-head attention and effectively predict the properties. And we did that. We compared our results compared to all these classical neural networks that you can see, for example, LSTMs. And what you can see is that, I mean, we were able to increase the accuracy and create a gap. So for example, the best ones was 84 or 85% at maximum 85.7. We were able to increase the 3%, and actually that 3% is a lot. Because I mean, usually the amount of changes in the data sets, changes in the accuracy of prediction is not that much. We did also ablation study. There are different ways that you can do this augmentation, right? So for example, you can randomly replace an amino acid letter. You can randomly delete it or replace it with alanine, because alanine is very naive, so you can use that. So there are different ways that you can effectively play around and augment the data set. Another work that we did with the protein language model is learning about the sequential design of the proteins themselves. So what we did is that we got a data set of GPCRs, G protein coupled receptors, which, as you know, I mean, is one of the most important drug targets. And then we were thinking about, like, is there are certain conserved motifs, for example, such as CWLP or DRI or NPXXY. And we were thinking of, like, is it possible to find out some relationship between, for example, the binding pocket of the protein, the amino acids here, and, for example, the differences that they make, for example, in these conserved motifs. So the XX here is LY, but in other places it might be something else. So we wanted to know some kind of, like, the philosophy between for the sequential design or the evolution that caused, for example, this relationship between binding pocket and some specific locations in the sequence of the proteins that are interconnected. And these are long-range dependencies, so they are not that much easy to interpret. So we thought that the protein language models can help us quite a bit. And actually, that was really interesting that we found out that, for example, there are a lot of correlations between certain parts of the switches or amino acids that are in the intracellular part of the protein and the small molecule binding pocket. And then we found out that actually we can predict the XX with a high confidence, for example, 98% test accuracy, if we know the binding pocket, for example, amino acids. And that makes us sure that, yeah, there is a kind of like connection between these motifs that are down in the protein, and they are connected in the way that the message is relayed from the small molecule to the protein. And we showed that how these are connected. So, for example, as you can see, these motifs here in the protein are connected to the motifs here, or there are amino acids in the fingerprinting region of the proteins, receptors that are connected to the another part, and we proved that part. And for some of the last part of my talks, I wanted also to talk about you can build any type of GPT, for example, antibody GPT, in which you give a small part of the sequence of, for example, antibody, and you talk to the language model for the proteins, and actually design or generate the G for the GPTs generate the different types of protein, actually antibodies. And for that, there is this foundational model that we call Protein GPT-2, which you can download it from Hugging Face, and then you can go ahead and find out different kind of antibodies in the assays. For example, there's a BCR, natural BCR data set, and you can go there and fine tune the ProGPT-2 to those type of models. And there has been a renaissance in the antibody discovery since the language models came into existence in 2021, 2022, and 2023 and 4. For example, one of the most important ones was anti-Berta, which is capable of deciphering the language of antibodies using self-supervised learning. So the technology is self-supervised learning, as I explained, and you can build a language model. Protein GPT is also one of the interesting models that is able to generate the protein sequences for you. Like when you're asking a chat GPT a question, it generates the language. When you're asking, for example, Pro GPT, when you give a small amount of sequence, it's continuing to build the rest of the sequence. And then the results for Pro GPT showed that it is consistently, if you give, for example, the initial part of the sequence of a protein, is capable of generating the rest of the protein sequences. I'm not talking about the AlphaFold, I'm not talking about the structure, I'm talking about the sequence design effectively. So we took advantage of that, and then we said that, okay, if I wanted to design an antibody, for example, for HIV or COVID, what you can do is that you can take some part of the light or heavy chain and use like 2, 3 starting amino acid of that fragment, and then you can use that as a guide to design the rest of the protein, to design the antibody effectively. So, for example, we use these three amino acids like QVQ or Q and QVQL, and we wanted to see that how good we are in the design of uh, most frequent actually starting amino acid letters for heavy and light chain. So we found those because instead of asking a question from ChatGPT, you want to feed these 3, 4 letters of amino acids to the protein GPT and design your antibody. So we wanted to see how effective is that, and then we use that for the prediction of the amino acid, for the prediction of the antibody sequences, and we got decent results. And then we found out that we can design, for example, that binding region of an antibody using the protein language model, and then we send it to the AlphaFold in order to see that if the structure that the protein GPT that we are designing the antibody with is consistent with the structures. And we found out that the structures are good. Another thing that we test for different antibodies that we design is the diversity, because if you're copying the same things almost that you're designing, is not a good thing, right? I mean, you're just copying. So it should be a diverse set of new amino acid sequences. We also check for the against the other repertoires of BCRs, and we saw that they are pretty actually diverse in terms of they are not the repeated amino acid sequences that are in the data set, but they are different. We checked also for the human-like sequences. We saw that actually this antibody GPT that we designed is effectively creating a very similar human-like sequences. So it is diverse and also it's human-like sequences. And it is sometimes oversampling versus gene families. So we did the benchmarks there. These are a little bit more details. I don't want to uh, make you tired of like, I mean, super details, but there are some challenges here as well that sometimes you have, for example, class imbalances or the distribution is imbalanced. So that is wreaking havoc with the model. So we are trying to actually create some remedies for that. I just wanted to conclude with the framework that we are working right now in my lab for the drug design. So we are creating some kind of LLM agent now, um, effectively, which is similar to a research scientist. And effectively, what it does is that it is communicating with the literature. It is searching. For example, you say, design for me an anti-cancer drug. So it goes and search the literature. It goes and talks to the generative models to generate a small molecule candidates. Then it sends it to the simulations, for example, molecular dynamic simulations or DFT, or it sends it to the wet lab effectively to do the experiments. Has also design of experiments backbone, and then also it connects to the data sets and models and APIs that are already available. And it checks everything. So it's kind of like research scientist who does the research. And this is being developed. We are almost 80%, 90% done with this. We'll publish the paper. This is kind of like the time for agents. So LLM agents like ChatGPT can go and monitor and actually supervise multiple AI models and also the lab in order to achieve an optimization goal or, for example, a certain goal. So the time this year 2024 and 2025 was about that one. So, for example, you can say anti-gene sequence designer, for example, a sequence model for me for antibody, and then it goes and use molecular modeling agent. It does an optimization agent. There are multiple agents that are working together. Okay, I think that's all I have today for my talk. Um, this is my lab. I just highlighted the work of some people that are working in my lab on these efforts, and thanks to the funding agencies, and I would be happy to take questions at this point. Thank you, everyone.
Thank you for the fantastic talk, Professor. Several questions came in. One of them, I'm going to read it. Did you conduct any molecular dynamic simulations for these newly generated compounds against a target protein?
Yeah, we didn't do any MD simulation. Actively, we just send it to AlphaFold to see that if the sequence that is designed effectively can be folded to a structure that is valid. But you can run the MD simulation in the pipeline, the framework that the AI agent has. So after you generated, for example, a molecule, you fold it, you fold the protein. We wanted to do this, for example, atomic simulation, MD simulation for the physics-based interpretation. And that's what I was doing actually during my PhD and postdoc. I was running a bunch of MD simulation for proteins. So that's also in the pipeline. But most of the MD simulation is needed for mechanistic design and understanding. So you wanted to understand why this amino acid rotates, or why this is folding like that, why the structure is like that. So that is also needed. And I think with this agent, it is gonna, if it doesn't understand anything, it sends automatically a kind of like MD simulation. And we are also creating something called, for example, LLM MD, which you don't need to create, because one of the difficulties with MD simulation is that PhD students and other students should go and make an input file for the MD, structure. Actually, that is also we are generating using LLM. So you only, like that agent is working with this agent together to send the simulation, get the results and trajectories, and then post-process them and get inference on them, like what does it mean, even like analyze the post-processing data.
Thank you. A second question came in. Like a language model, is it possible to understand the properties of a combination of blocks in the same way that we interpret a sentence? Meaning, how we understand a concept and get impression of a bunch of words in a sentence or a text.
Exactly. That's what we did here. So there is something in the transformer called attention head. And attention head is beautiful. Why it is beautiful? Because it's very interpretable. What does it do? The whole transformer idea is based upon, let me show you here, is based upon like attention of the context. So in the language models, when we are writing a sentence, effectively some words are attending to uh, some other words, and some of the other words are not important in the context. So in that way, if you look at the attention heads in the transformers, and there is actually a package called visualization of attention heads. And we use that here. So in the GPCR BERT, if you look at the paper, we were looking at the attention heads here, attention weight, you can see. And we look at like to see that, for example, these amino acids here, where they are attending to. So which amino acids here, for example, NPLIY, what it is talking to. Does it talk to like VTAS or does it attend to this one? So with that, actually, you can find out the biological connections between different parts or segments of amino acids. And that's a great way of interpreting. So that's why, I mean, we said GPCI BERT, and there's also a ICLR paper called protein Bertology. So using BERT, you can do the philosophy of like the design, evolutionary design of the sequences. So yes, that is completely possible with the transformers.
Thank you. And another question is, can you apply the GPT in protein-protein interaction prediction?
That's an amazing question. We haven't done that, but I assume that what you can do there is that here, so you will have a GPT that is sequencing. Actually, you can send the sequence of the first protein. You can use the sequence, encode the sequence of the first protein, the second protein, get them in the latent space. And then if you have, for example, the binding affinity of the protein-protein interaction, you can fine tune with adding like 2 layers or 3 layers of neural networks by concatenating the latent space of the first protein and the second protein and sending it to like 2, 3 layers of neural networks and fine tuning that to the protein-protein interaction, actually protein binding affinity or something like that. I think that that should be possible to be used for protein-protein interaction as well.
Thank
But
you.
we haven't done that.
Thank you. Another question is, how to use your LLM agent if we have the protein sequence?
Okay, so how to use the protein, that's great. So I mean, my philosophy, the way that we are working here is that you can send, for example, the message to the LLM agent, hey, LLM agent, I want you to design an anti-peptide, a peptide with anti-cancer property. So the LLM agent send a message to our, for example, peptide GPT, and it generates some sequences. Then the sequences that you have, you don't know if they are folding or they are valid. So it's going to send it to molecular dynamics simulation, and then it's going to see if it is folding or it sends it to AlphaFold, and it looks at some of the properties. There should be another arrow here to the CROs or like, I mean, the test beds. Now that these sequences are good and you have the top candidates, the agent is going to send it to the wet lab to measure their properties. For example, properties like aggregation, and then it can get the test result from the wet lab, and analyze it and put it in the database if it worked or not worked. And then it can learn effectively from this cycle of experiments that what should be the next sequence, what are the ways that it can give a prompt for generating a new sequence to make it better and better. So it does the design of experiment in the loop as well. So that's the way that we are working right now, that the LLM agent is actually supervising multiple AI models and also other agents together. And it can communicate both with the simulation and the experiments.
Thank you. Another question is, you mentioned about antibody design using your program. How about aptamer design, either yourself or other people?
Yeah, I mean, I didn't see Optimer design, but with the same framework, it's completely possible because Protein GPT is effectively the general engine for protein amino acid sequence understanding. So anything that is related to a protein, peptide, antibody, uh, receptors, whatever protein that you think about, you can design it. The way that you can design is that you just need to go and find an Optimer dataset and fine tune it to the Optimer dataset. And effectively, you can have your Optimer GPT built as easy as that. That's not that much difficult.
The final question is, you mentioned that the companies were resistant in having or providing 200,000 data points. And you said you can reduce it to 381. Then you said your pre-training, you still need 1 million data points.
Hmm.
Where do you get those million data points? Isn't
That's
it?
a great question. So the million data points that I said mentioned here is unlabeled data. So there is a difference between data set that are labeled. I mean, like the companies are resistant in giving the labels. They are not resistant. Actually, they can't do it, right? I mean, because it's very expensive. Each experiment takes thousands of dollars and a few weeks, right? When you say 10,000 or 100,000 experiments, then they refrain. Why? Because I mean, they can't do it, right? But if you have a pre-trained model, and these pre-trained models are run on the unlabeled data, these are only polymer chemistry. And those are abundant. I mean, we have tremendously large amount of data that is available that they don't have labels. Where can you get them? From PubChem, from PDB data bank, from different resources online, okay? Like here, you see, it's growing. And these are without the labels. So you can see that you have 60 million molecules. But out of these 160 million molecules, perhaps a super small fraction of them have labels. But you do the pre-training with this amount of data with the unlabeled one, and that makes it very easy for you for fine-tuning, or effectively, it requires less number of data points during the fine-tuning. And that was my point. Effectively, at this stage, after you do the fine-tuning, so after you do the pre-training, you have this network. For the second network that you transfer the weight, you only need a fraction of what you already needed. And that fraction is like 200, 300 data samples. And now, if I go to a company and I say that, hey, I wanted to build a machine learning model for predicting a polymer property that you desire, and they ask me how many data points you need, I don't say 10,000. I say like 200, 300, and they become happy. 200, 300 is very doable. I mean, they can do it like in a month or 2 months or 3 months. And that was my point, effectively, to give me the 200, 300 uh, data points or molecules with with labels.
Thank you. Appreciate it. The final question is maybe a naive question. You mentioned a lot about ChatGPT. Are you utilizing ChatGPT in your research, or are you using similar algorithms to ChatGPT for your predictions?
Both, both. So first of all, like the transformer, we are using the architecture. So for example, in the transpolymer, this is our own design. This doesn't have anything to do with the chat GPT, but it is using the T of the chat GPT, which is the transformer, the idea, the model. We are using the P of the chat GPT here, the technology. So this part of the talk is the technology of chat GPT. But the agent that we are designing, the agent that we are LLM agent that I talked about, is actually the LLM agent is this agent. This agent is ChatGPT. So is it ChatGPT or Llama or DeepSeek or whatever, which gets the data and communicates with other AI models? That's ChatGPT itself.
Excellent. Excellent. One final question came in. Thank you so much for a great talk. Have you compared your transformer-based model for polymer property prediction with other types of deep learning architectures, such as graph neural networks?
It is beating them, all of them. Yes, we did it. I don't know if I have the benchmark. So this, yeah, so this is the best baseline. Okay, so the best baseline was graph neural network. You're right. I mean, like the best baseline, and uh, and look at that, the transpolymer. So this is the amount of error. This is the best. I mean, so this is the amount of, like, if you get the differential, it's like 22% better compared to the to the to the to the best model available there. Yeah, you can look at the paper. The paper is in is Nature Computational Material Science in 2023. You can find it there. But I mean, yeah, it is beating them not only because of the transformer, but also because of pre-training. It's not only transformer. And transformers and pre-training are like peas and carrot. They are working beautifully together. I mean, the amount of like how good, I'm super surprised at how good pre-training is working with transformers. Pre-training might not work super well with the graph neural network, but it is working like a charm with transformer. They are dancing together.
Thank you so much. That's all the questions I have. Thank you for your time, Professor.
Thank you so much for the invitation. I really enjoyed.
Thank you.
Thanks.
Nice day.
Bye.